In this video, we will talk about properties of probability measures. So I'm going to get right into these properties. So the first property, before I write down what it says, I'm going to draw a picture. So I'm going to draw a Venn diagram, and I'm going to draw a circle for the event A. In fact, let me put the A inside of the circle, and then I'll put that inside of our universal set. So I'll call this U, or in the case of probabilities, our universal set we can also indicate as S for our sample space. And so the complement of A would be all of the stuff outside of A. And we know the probability of the whole sample space is supposed to be 1. So based off of this picture, the probability of A plus the probability of A complement should be equal to 1. So if I rearrange this, we get the first property, which is that P of A equals 1 minus the probability of A complement. Okay, so this is something that we've seen before for equally likely outcomes, but it's going to be true even for more general probability measures. All right, so property 2 says that if we have events A1, A2 up until AK, and they are pairwise disjoint, then when we look at the probability of A1 union, A2 union, and so on up until AK, so union of all of these. Before I state what it is, let's draw a picture. So I'll draw a Venn diagram, I'll have a circle for A1, a circle for A2, and I'll draw A3, and then maybe there's some more, so I'm just going to put some dots, and I'll have a circle for AK. All right, and now let's draw a rectangle for our universal set U, which I can also call S for my sample space. And we can see from this picture that, kind of conceptually, if we wanted the probability of the union of all these sets, and they're pairwise disjoint, the circles overlap with each other, then the probability of that union is just going to be each of these probabilities added up. So the probability of A1 plus the probability of A2 plus plus the probability of the last set, AK. Okay. All right, so one more of these properties, which says for any events A and B, if we look at the probability of the union of the two events, so now they don't have to be disjoint anymore necessarily. And I think you might see where I'm going with this if you remember what it looked like when our events were not disjoint in our general Venn diagram before in chapter 1. But if I draw a circle for A and a circle for B, within my universal set U, which I can also call S for my sample space, the set of all possible outcomes. Then when I find the probability of this union, if I do the probability of A, that is going to sort of consider everything in this circle for A. And then if I add to that the probability of B, that is going to add up, that is going to end up adding everything in the circle B. But when we do that, we've actually counted the stuff in the intersection of the two circles twice. Okay, so we don't want to count it twice. We only want to count that intersection once. So we have to subtract away the probability of the intersection so that we only end up counting it one time. And that is our third property. So let's highlight all of these. So here's the third property. Here was the second property. This is when our events are pairwise disjoint. And let's scroll up to the first property. Whoops. First property was to find the probability of the complement. Alrighty, so let's look at an example next. Alrighty. Okay, so this example says let A and B be events in the sample space S with the probability of A being equal to 0.41, the probability of B being equal to 0.55, and the probability of the union of A and B being equal to 0.7. Find, part A asks, the probability of A complement. So let's draw a picture. So I'm going to draw a Venn diagram, and I'm going to draw a circle for A, and let's put that in our rectangle for our sample space. This time I'll just call it S. And the question says that, well, the probability of A is 0.41. So the complement of A is going to be the stuff outside the circle. Okay, and I know that the whole sample space's probability is supposed to be 1. Okay, so the Venn diagram here just helps me visualize what I'm going to do to find the probability of A complement. I can see now to find the probability of A complement, I just take 1 minus the probability of A. So I got to do 1 minus the probability of A was 0.41. And if I work that out, we are going to get 0.59. And in fact, that is the probability of A complement. If I add 0.59 to 0.41, I get 1 like I need to. All right, let's look at part B, which asks for the probability of A intersected with B. So let's draw a Venn diagram here as well. This time I'm going to have 2 circles. So one for A, one for B. I'm making them overlap because the problem didn't say anything about them being disjoint. And I'll draw them within a rectangle for our sample space. Okay, and I want to know the probability of A intersect B. Well, so I can start off with my formula for probability of A union B. And that's equal to probability of A plus probability of B. And then minus the probability of that intersection of A and B. And now let's plug in for what we know. So we know for the union that probability is 0.7. The probability of A is 0.41. Of B is 0.55. And then we're going to have minus the probability of this intersection. Scoot it over a little bit more. Okay, and now if I rearrange this and move the probability of the intersection to the left, it becomes positive. And on the other side, let's see, 0.41 added to 0.55 is 0.96. So we get 0.96, and let's subtract 0.7. And working out what that is 0.26. That is the probability of being in this intersection. So let's do one more part to this example. Alrighty, so this asks for the probability of A intersected with B complement. Okay, so A intersected with B complement. Let's draw a Venn diagram again. So I'll have A, we will have B, and let's draw the sample space. And I already know the value for the middle, it's 0.26. We worked that in part B. So A intersected with B complement means that we are in both of these. We're in A, and we're in B complement, which means we are not in B. So that is talking about, let's see, which region? That is talking about the stuff that's in A and not in B. That is this whole section. In A, but not in B. We're trying to figure out the value there. So I'm going to label my work. So we are going to focus on the circle A. And focusing on that circle, if I think about the probability of A, it should be equal to 0.26 plus whatever value goes here. So I'll put a box there. And the problem told me the probability of A was 0.41. So that equals 0.26 plus this missing number. And if I do a little subtraction, I will get that this is 0.15. And that goes here. And that is my answer. That is the probability of A intersected with B complement. It is 0.15. So in terms of our goals for this section, we have finished our second goal, which is talking about how we can apply those properties of a probability measure to working out some examples.